Module 1, Lesson 5. How many different substances can you think of? A lot, right? All of these images that are going around the screen are different substances. They're made of different materials. In fact, there are millions of different substances on this planet. And I bet if you looked around you, you'd easily spot at least 50 just by gazing around. All substances or materials are made of very tiny particles called atoms. We usually depict an atom like this, where you've got the nucleus here in the center that's made of protons and neutrons, and out along the outside, whizzing around, are these electrons. Now, this is not an accurate drawing because there is a heck of a lot more empty space between the nucleus here and the electrons. In fact, if we were to draw this to scale, we would need a piece of paper the size of the stadium. The nucleus would be a little marble in the center, and the electrons would be bouncing around way out on the outskirts of the field. So the next time you stand on something hard or knock on a door, think about it. It's mostly just empty space. Now, atoms are what makes up everything. Atoms are organized into about 120 different types of elements. Now, to explain the difference between atoms and elements, we're going to take a look at a car. So this here is a basic car. It's got your wheels, an engine, steering, braking, seats, trunk, etc. It's got all the parts of a car. Now, there are different brands of cars or different types of cars, and they go by names: Ford, Dodge, Toyota, etc., etc. Now, to compare this to the atom versus the element, which do you think would be most like the basic atom? The basic car or the different brand? Chances are you might have said atom, and if you did, you got it. The atom is the basic, which means the brands are like elements. They're specific types of atoms. Now, to look a little closer at the elements, an element is a substance made up of only one type of atom. So here we got a copper pot. If we were to look really closely at that, we'd actually see that it was all the same particles in there, all copper. So copper is an element made up of only copper atoms. Carbon in the form of coal here. Again, if we were to zoom right on in there, we'd see that all the particles, all the atoms, are carbon. Hence, carbon is an element made of carbon atoms only. And once again, helium, if we look inside there, we'd only see helium atoms. Helium is an element made up of helium atoms only. Elements. 2. Elements are the building blocks of all other substances. So everything you look around that you can see in the form of matter is made of these atoms. They're the building blocks, like the Lego pieces. All elements are listed on the periodic table. All elements have been given an official symbol, and you can find those on the periodic table. So let's take a bit of a look at the symbols. So generally, the symbol is the start of the name. So for example here, carbon symbol is carbon. Aluminum is Al. Can you think of any other symbols like this that you know from the periodic table? Maybe oxygen, nitrogen, fluorine, chlorine. Now, note that the first letter of an element's symbol is always a capital. So example, nitrogen would be a capital N, not a little n, just as we see in carbon here. Or if there happens to be two letters, which some elements have, the first letter is a capital, second's lowercase. So for example, cobalt down here would be capital C, lowercase o, and just as we see up in aluminum, capital A, lowercase l. Now, not all symbols are the same as the element's name. So a couple here, ones you'll get familiar with are sodium, which is Na, and potassium, which is K. But it does follow the same convention. So, like in sodium, capital letter, lowercase, potassium, if it's just a single, capital letter. So, symbols are important. Symbols are important for a couple of reasons. The first one, elements have different names in different languages. So for example, in Russian, nitrogen is called azot, and iron in Portuguese is called ferro. Therefore, to avoid confusion, symbols are used. They're universal. Symbols are quicker to write than names. So I'm sure you've all seen a chemical reaction or a chemical equation, and in there you see symbols. Imagine if we had to write each word out. It would take too much space and time. We also can use symbols to denote in drawings that we may do of a molecule. The International Union of Pure and Applied Chemistry, short, IUPAC, a lot easier to say, it's the governing body responsible for the systematic naming of elements and compounds. Okay, moving right along here. In some elements, the atoms are joined in groups of 2 or more. A particle containing atoms grouped in this way is called a molecule. Now, on the periodic table, there are 7 elements that are always found as molecules in their pure state. One example is oxygen. Oxygen is an element made up of oxygen atoms only. How many atoms are there in an oxygen molecule? So if we go over here, we can see 1, 2. Oxygen is not the only element that is in 2s when it's by itself. There are a total of 7 that are found in pairs when they are left to be alone. So these are called diatomic molecules, and they're elements that in their pure form are found in pairs when they are alone. The 7 diatomic molecules are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So looking at a square from the periodic table, there's 4 elements I'm going to look at here. Some squares, most periodic tables have a bit more information, but this is just some basics. The top left, or even sometimes center or right, is what's called the atomic number. In the middle is a big letter or letters, and that's the symbol of that element. Below that symbol is what's called the atomic mass. And then somewhere on there, often at the bottom, sometimes the top, you'll see the name of that element. Now, down here, back to the diatomics, you'll see the 7 diatomics laid out here, starting with the smallest of hydrogen. You'll note that they're all in 2s. You'll note below is a representation of how these atoms would be joined in a bond. So you're either going to see a single line, triple, or double. These represent the bonds between them. Hydrogen has a single bond, and you probably guessed nitrogen has a triple bond. Below that, you see the name and the symbol. So the symbol comes from this periodic table. So oxygen is right here. So O represents oxygen, and the subscript 2 represents that there's 2 oxygens in this molecule. So pretty straightforward. Now, a couple of tips to remember these 7 diatomic molecules. You are going to need to remember them, especially if you go on to chemistry. So here's a nice mnemonic device. Have no fear of ice-cold beer. You'll note that the beginning letter of the mnemonic matches the beginning letter of one of the diatomic molecules. Or this is another clever way using the periodic table. Recall there's 7. The start here, you can start with atomic number 7, which is nitrogen. And then look at this. It makes a 7. 3 across, and then go down another 3. You just have to remember hydrogen over here on the left. Now, one thing to keep in mind, these elements are in pairs only when they are found by themselves. So they can combine in different ratios provided another element is present. So for example, we got carbon monoxide here. See that? Only 1 oxygen. Or chlorine trifluoride. Look at that. 3 fluorines and only 1 chlorine, right? So it's only when they're found by themselves. Okay, periodic table. Let's take a little look at that. The periodic table is more than just a reference sheet. It is a list of all the known elements to humans. So you can think of it as an ingredient list of the universe. There it is. So that universe is all on that piece of paper. The periodic table has some amazing trends that appear based on the size of the atom, the periodic as in it repeats itself. The size is also based on protons, which we'll get into more in the next module. But here is just one such trend that I want you to take a look at. It's the breakdown of what type of element we have. There's either metal, metalloids, or nonmetal. So let's take a look at metals. Metals are on the left and in the center of the periodic table. They're colored pink on the table below. Metals make up most of the periodic table. Metals are generally shiny, malleable, ductile, conductive, both electrically and thermally, as in heat. And all of those metals at room temperature are solid except for mercury. Now, nonmetals. They are mostly on the right, mostly because hydrogen is on the left of most tables. Nonmetals are colored green on the table below. Nonmetals are pretty much the opposite of metals. So therefore, they're dull, they're brittle, they don't conduct heat or electricity, and at room temperature, they can either be solid, liquid, or gas. So you've got a variety there. So here's just some example. Carbon's a solid, these guys are powders. Okay, metalloid. Metalloids are located between the metals and the nonmetals, so they're colored yellow here. Metalloids sometimes behave as metals and sometimes as nonmetals, hence the name. Now, the interesting thing about metalloids is there's really no standard definition because they behave kind of as both. And to be quite honest, there really isn't a standard agreement on the elements either. So for the purpose of this class, we've chose this little strip right here, which is the most consistent of the metalloids conclusion out there. Okay, so I hope you found this video useful. Don't forget to continue with the rest of the activities, and I'll talk to you later. Thanks for coming out.